Okay, good morning. Before the class, I just want to mention we got this assignment 4 ready in the last several days. We already got lots of discussion in Piazza. If you look at the due date actually is the last day of the class. Okay. It simply says we make assignment 4 and assignment 5. There are a total of 2. One is a programming assignment. One is a written assignment. Okay. And these 2, because the programming assignment usually will take a longer time, that's why we got it more. If you look at the time, we get more than a month. Okay. It doesn't mean you can relax. You should start early, because usually the programming assignment will take you longer time to not only understand it, but also try and error many rounds. Okay. If you look at this assignment, the same thing is we do allow you to use multiple programming languages as before. Okay. And we did set up a late penalty, because last time we got a few students, they missed the deadline. They say they got a bugs they cannot handle, whether we give them 0 point or we give them, some point they have tried so hard. So finally we decided to extend the deadline for 1 day to handle these group of students. They really struggle there. But in the meantime, we discussed with TA, we set up the late penalty. That means if the students struggled, we don't want to give them 0. We allow them to work 2 or 3 more days. Okay. Then that also caused some students that I tried so hard to beat the deadline, I did not get extra points. But some students tried it, they got struggled, they got a 1 day extension. It may not be very fair. And then we finally decided for this last programming assignment, we will not get any grace period, like a grace 1 more day. Okay, simply says I tell you beforehand, long beforehand. Okay, then what you need to know is if you really got stuck somewhere, you do have, chance to still submit, but get some penalty. Simply says you get 1 day late, you get 10% penalty, and 2 days late, you get 2 days, you get 20%, and the 3 days, you get 40%. And we won't accept it, even later one, because later one, if we set up 80%, it doesn't really make too much sense anyway. Right? So we probably, plus this time, the TA really need to wrap up the whole class, the whole course. Okay? So make sure you start early. You get any problem, we set up all the office hours. You can come to TA's office hour or my office hour. Of course, this detailed assignment was worked out by TA. You probably need to discuss TA more than discuss with me, because I can give you the principles. But for some particular data sets or particular tricks, you probably discuss TA, you get more benefit. And if you look at this, essentially we have some classification methods ask you to play. Okay. Simply says we have decision tree and a random forest, and we also have naive Bayes and A doubles. Okay. So you really need to play with a few most popular used classification methods. Okay. The decision tree, instead of using information gain, we ask you to try Gini index. Okay, so that's comparing to the previous, some years ago, we did ask you people to do information gain. The TA also was afraid of whether anybody got a few years ago assignment, they try to copy it or something. That's why we have to change. Okay. So we change it to Gini index, simply says you have to understand the different measures. Then I believe it's enjoyable in the sense you learn the general principles of classification. If you do not really do it using the real data sets, your understanding, no matter what, your understanding could be shallow. Once you do it, really see the real data, how it works, you really learn it. So you get any problems, you can come to my office. If it's a common problem, you can post it in Piazza, then we can have more discussion. Start early. Okay, that's all the things. Another thing is we also asking you to do multi-class classification. Simply says not just a binary, 2 classes. We may ask you to do multi-classes. So that's the difference from the previous. If anybody see the previous assignment, we only ask you to do binary. So simply says you need to carefully go over this. This one essentially covers most of the basic parts, but cover in a solid way. Once you finish the assignment, you really understand the chapter very well. Okay. So that's about the program assignment. If you look at the timeline, actually a few days later, we are going to give you the written assignment. The written assignment will be more on the advanced part of the classification and the clustering. Okay. That's the last one. And the due date is the same time. Essentially, it's the end of the class. Okay. It simply says, by closing to the end of class, you will have more work. So it's better you start early, especially for program assignment. You do it early, you don't have to rush at the end. So we strongly suggest you start now, and you get any problem, we try to help you at all the time, okay? Including the Thanksgiving break. Okay? Now we will continue our discussion on the neural networks. Last time we give you the general idea about this neural network is you got a lot of things connected together. And you have one layer we call input layer, one layer we call output layer. But in the middle, we may have one or more hidden layers. Here we just draw one, but in most neural networks, you have 1, 2, or 3 is very popular. Okay? But for deep learning, you need more. Okay? Sometimes you can get even more than 10 layers. Okay? So, but the typical neural network is 1 or 2 layers. And the information flow is you start from the input layer, you go through the hidden layers, and you go reach the output layer. You move forward. Information is propagating forward. But on the other hand, if you got a training data, the training data check the output. If you get an error, they're going to propagate back to change the weights of the links. Okay? So that portion, the learning portion, the adjustment of weight, is propagating backwards, so we call back propagation. Okay? So that's a general idea about this, how the neural network works. Okay? The network topology usually is you have one or more hidden layers. And you have one input layer, and you have one output layer. Then you have lots of weights attached to, to all the connections. So that's the neural network usually trained by adjusting the weights. So now we see a little on the back propagation. We said you train the neural network is based on you give some feedback at the output layer. Okay? That means originally, when you assign the weights, you can assign everybody got the same weights, like everybody got a 1, like in the beginning. Okay? But while you get this output, the output will check your prediction, your classification. You can think about whether you classify this input as 1 or 0, okay, in that way. While you get this, you will see your prediction has a gap between the real label. Okay, that means you have an error. The arrow, actually, what you want to do is you adjust the weight, try to minimize the mean square error. Simply says, you adjust the weights to make sure your training, you go through this again, the training, you will have less errors. That means it's closer to your output given labels. Okay? So that means you try to minimize the mean square error. And how do you minimize it? Is you based on the arrow, okay, you propagate back. Propagate back means you actually say, here there is too big difference between your prediction and my label, so the error gap is bigger, so you go back and adjust the weights. So adjust the weights essentially, remember every neuron is essentially is a nonlinear function, right? The nonlinear function, you based on the error rate, you can adjust the weight to make sure your nonlinear function will go closer to the prediction. That means it will reduce the error. Okay? So that's a way you can adjust the weight. Okay? That means initially you can give weights to some small random number associated with a bias. Okay? Then you propagate information forward. That means you use your input, you move forward based on your weights, go through the hidden layer, reach the output layer. Okay. Then the output layer you find is different from the class label. Okay. That means you find the error, you propagate the error by update those weights and biases. Remember, if you go back to the previous single one, you can see is you have the weights, you calculate this one is the bias, okay, and that's the output. Your output is different, you get an error rate, then you adjust these weights and adjust this bias to make sure it's closer to the output. Okay, so that's a learning process. That's for every neuron you do this. Okay. So that's the general philosophy. You propagate back on those arrows, you adjust the weights, you update the weights. Okay. Until when? Until you will not be able to improve it. That means you may go back and forth many rounds, and until you said, so far, based on the current label, current training set, I cannot improve anymore. Okay. That means the error is very small. Then you can terminate. Of course, the usual training will take a longer time because you go back, you adjust the weight, you try it again, you still find there are errors. Then you will retrain it. You do it many rounds, and that's also why the neural network training will take longer time. So that's the one. Now of course, you get into detailed computation. There are many, many different training functions and many different topological structures. I will not, in this short coverage, I will not give you all the different things. Okay? You can go back and read lots of research papers or articles. Actually, there's one Coursera course done by Andrew Ng. Okay, now, later, he was also Coursera CEO or something. Then later, he actually went to Baidu, another company. So then, but he was a professor in Stanford. He gave a course on machine learning. And because he's very specialized on neural networks and deep learning, he covered that one in his course in much detail. If you want to know more about this neural network and deep learning, you should go to Coursera to watch his video. His video is also completely public. And what is the difference between neural network and deep learning? Okay, deep learning a lot of people say deep learning, just a deep neural networks. What is deep? Deep means you get many layers. You remember most of the neural network has 1 or 2 layers. Okay? But you get deep, you can get 10 layers or even more layers. Okay? Actually, for anything over 10 layers, most people call these ones very deep neural networks. They put a very deep, simply says most deep neural network. They are deeper than 2 or 3. but they are not as deep as 10. Okay. Of course, it can be more than 10, and they call these very deep neural networks. And for different layers, why the different layers? They can improve the performance. The general philosophy is different layers, you are looking for more and more structured and more complicated features. Okay. You can think the first layer, for example, for image processing. The first layer, they usually learn the first order features. For example, edges. You try to recognize the edges in the image. The first layer probably will help you to analyze and recognize edges. But the second layer, they can learn higher order features. For example, you can combine those edges, become some kind of structures, more complicated structures. So the second layer. Then you can go more and more layers, you learn more and more complicated structures. And some, you can say, the first layer, you just, for the word to vec or something, you learn this, you can say, you just learn the very, very close ones, neighbor, immediate neighbors. Then you get a deeper layer, you learn longer distance ones. Okay. So that's the one. But I'm not going to discuss in detail on deep learning, because that one itself is, it should be a course. Actually, I myself haven't seen a very systematic deep learning textbook yet. Okay. I just ordered one. They say it will be available in December. Okay. So, so far, maybe you really want to learn this, you should go down to some tutorials. People are really working on this. Actually, yesterday I was in Toronto. Jeff Hinton was a professor in University of Toronto. Sometimes he's in MIT. He is the one who worked on this deep learning or deep neural network for many, many years. When I was in Canada, I actually know he was a professor working on neural networks. Until recently, he got really famous. He did lots of talks as well. That's a deep learning. I probably will have my limited capacity, to cover this. Plus, our course is very broad. So I will just say, the deep learning, you learn this. You can do it in unsupervised version or supervised one. Supervised one means you have a layer, especially in the output layer or closer to the output. You can put a lot of labor information there, then they can feed back. Okay. Then they can learn this. But they also, you can do it in a reasonably unsupervised version, like a clustering, those kind of optimization, some functions. But anyway, deep learning now is very, very hot and also quite useful. The reason is people around 2009, okay, I should say even before 2009, around this time, there were lots of competition on, for example, pattern recognition, voice recognition, or something. And they found this neural network is far better than many other learning models. Then people finally really recognized this one is very powerful, because with so many layers, you adjust those weights, you actually can recognize something, other functions, other methodologies, hard to do. Of course, it takes time, but nowadays you have GPU, you have lots of different processors. The time is not a major factor, because you can first train it. When you use it, you don't have to retrain it. It's just based on trained model, so it still can be very fast. Just give you an example. If you, for example, in the university, you call a professor or call a secretary, they record the message. They actually automatically transcript it. And who transcribes it? It's machine. Okay. Essentially, it's those neural network algorithms. Sometimes, of course, it may make mistakes. Okay. But in many cases, the transcripts capture a lot of major essential points. Actually, sometimes I traveled, they left some message on my phone. I actually read the transcripts. They are reasonably accurate in the sense, at least I know what they're talking about. Then whether it's commercial or it's something serious, I have to listen to. Okay, so that implies those things really works. If you got the most recent version of Mac, they have something like a Siri. You actually can talk to them. They can actually you don't even have to type. Sometimes you can talk, they can understand. That implies they really can get these kind of neural network can learn something. Okay. So voice recognition, some automatic image recognition, people are thinking this deep learning is very powerful. But I will not give you a detailed introduction. I should say later, if you really want to learn it, you should get into those deep learning courses. On this campus, there are quite a few group of professors very interested in get deeper into this deep learning. In the future, they will systematically teach this kind of materials. Okay. So it will be either in computer science or ECE, because I saw the group of people. I was part of it. I saw lots of discussions. They plan to open such courses in the future. So those about neural networks, I give you a very shallow introduction, but you basically know, conceptually you know what it is. Now we get into another one is support vector machines. Support vector machine is also very powerful, very useful. In early 2000, they think this one is the most powerful classification methods or classification engine. Okay. Nowadays, they are like a probability graphic model, and later get this deep learning. So the support vector machine may not be the only one, but it's still a very powerful one. Okay. What is general principle of this support vector machine? We probably should go back to thinking about a classification. The classification early days, people actually called the linear classifier or discriminant classifier before the support vector machine comes out. Okay. And what this one is people will think you do classification, essentially you predict a positive one or negative one, or you can think of predict 1 or 0 or something like this. You get a binary classifier. Okay. The binary classifier you can think is mathematically, you can think this way. You can think you got either a training set or a testing set. The training set could be you get a set of features like x1 to xn. Okay. Then you get a class label. Class label is positive 1 or negative 1. You can think it's like you got a cancer or not cancer. Or in the case whether you want to classify whether this web page is a person's home page, then you can say either either it's a home page or not home page. Okay, so you may have 1 or -1. Then you get a lot of features putting in. Some features are useful. Some features may not be useful. But you can think about it mathematically. You can think it's a mapping. The mapping means you get a bunch of training set, some sitting at the positive side, the other sitting at the negative side. Your classifier essentially is try to find a separator. That means try to find a boundary. You can draw this line, you will be able to separate nicely, in a sense. Probably majority things you can separate them into. You draw a line, you can separate this from classes. Then the key is try to find such a line. Okay. Finding such a line, usually you try to find a straight line, because the straight line means it's a linear equation. If you can draw a straight line, you can separate the two sides. That's the best. Okay. So if you can draw this line in the binary classification, they call this one is a linear classification. Linear means it's a line. Okay. Mathematically, it's a line. Okay. And if you can draw this line, you can find such a line to successfully separate the positive and negative class. Then you may get a good linear classifier. And actually, there are lots of linear classifier people work out, okay, including very early days. In 1960s, people work out one called perception. And then there are other probability classifiers, okay, like a discriminant classifier. And later, the most advanced one is support vector machine. Then we are going to discuss how these linear classifier move on to get into the support vector machine. Actually, before the support vector machine came, people actually work out a bunch of linear classifier. Most people call this one is discriminative classifier. Discriminative means you get this line, you can discriminate positive class versus negative class. Usually, if you can get such a one, the prediction accuracy could be high. That means you get a proper line to separate these two classes. Comparing with Bayesian, mostly just probabilistic model, and this one, the discriminant mathematical model, may have some advantage. Okay. Another thing is, if you can draw a good line, it is robust in the sense, usually the line can separate these training set. Likely you give me new one, even get a little noisy one, but I have a line reasonably clearly separate the two. I could be, not afraid of small noises. Okay? And also, it could be fast. Okay? The training could be fast. You just mathematically work this out. Okay? But on the other hand, to work out this function itself could be longer time. That means you need a lot of computation to finally work out this good line. Okay? This fast evaluation is testing, or is really usage. That means I train this model, I give you a linear equation. You put your new data in, the linear equation immediately return positive. That's fast. But training to get this line properly laid out will take some time, because you have to adjust your line back and forth many rounds. Okay? You need a lot of computation. Okay? Another thing is, those lines work out finally just weighting. You get different weights. It's hard to explain. Okay? It's not like decision tree, those things is very easy to understand. Okay? And also, it's hard to get a domain knowledge incorporated, because you know something, how to put it in is not clear. Okay? So that's the general about the linear classifier. Now we get into this support vector machine, which probably among those linear classifiers, this one is most powerful one. That's why they get into this so much attention, so much discussion. This general idea is you want to work out a good hyperplane to separate the scene. And you want this hyperplane to be easily recognizable, to have the most separation power. Okay? And then even for the nonlinear one, you may be able to map into even higher dimension. You may still find a linear one. Okay? So that's the power. Actually, this one was, if you look at this, the leading one, a researcher called Vapnik, he actually worked out this theory, the static learning theory, in 1960s. Okay? But it was not, attract lots of attention at that time until around 1990s, and people found the method is powerful, and the computation, you get more computing power. Computation is not a major problem anymore, and they have lots of new, like a kernel functions or something. Then it really took off. In 1990s, it became really hot, and people are using this in many classification tasks. And it can be used for many things like handwriting recognition, object recognition, speaker identification. Remember, those things, actually, nowadays, deep learning is a strong competitor. Simply says, they can do this now, the deep learning claim they also can do this, and they can do better. Okay? But support vector machine is still pretty powerful in classification. What is the general idea? Let's look at just a simple example. Suppose you got two classes. One is in those, orange color. The other one is in blue color. Okay? And you want to work out a separator to separate these two. Of course, I draw it in a way you just watch it, you say, oh, that's not a big problem. It's not a hard problem. But what we can see is the separator, even you can draw many different separators. Some separator is far better than the others. You work, visually you look at this, you can see the differences. For example, you can draw a straight line, vertical one. You say, I separate this one. But obviously, the vertical line is not a very good one. Because if you look at these two sets, even by visual, you look at this, the straight vertical, actually, equation-wise, it's good because vertical means that you ignore x value, just look at, you ignore y value, just look at x value, you can draw one. Right? But it's not a very good separator. Why? Because you think about this. If you draw a vertical one here, these two are so close. Okay. So close means actually this vertical one, you sway a little, you may change the label. That simply says you give me a little noise, and I will not be able to actually say which class it is. Likely you may make error. However, if you look at this angled one, this one is a very good one because you can see you have a very big margin, comparing to all the different classes. Simply says you try to draw one which is non-disputable. You sway a little, your different colors sway a little. My classifier still, can powerfully, unambiguously separate your two classes. Right? So that means you want to find such a line which give you the largest margin you can find to separate the two classes. And what is the largest margin? You probably can see these two things, these two lines. You see that there are three objects here in the blue class. There are two in the brown class or orange class. You probably can see these two lines actually are the, you can think are the two classes they are closest. Okay? And if you only take care of these two vectors, you try to work out line instead of thinking all the data. Okay? You just take care of these two vectors. You try to find the best separator, and you will be successful. Then people actually call these vectors, these orange ones, you get this vector, or these blue points, you get these vectors. They call these vectors are support vectors. That means they actually support you to get the best classifier. So these vectors are support vectors. And if you try to use those support vectors to work out the best margin, best classifier, that classifier itself called support vector machine. Okay. Actually, just the people's name actually is not a real machine, just a software or just a mathematical equation. It's an algorithm. Okay. But people in the early days they like to call this one a support vector machine. That's why you got this machine. It's nothing to do with our hardware. It's not a GPU, CPU things. Okay. It's just a mathematical equation. Okay. So then, if we know this, let's look at this one. Basically, say, suppose we still have bicomputer, yes or no. Okay. You map them into some mathematical space. Then you will try to find the largest margin, and that portion you probably can see. These points we call our support vector. So that's basically it's kind of linear classifier. Okay. Then how mathematically we really work this out? That's a major challenge. That means you give me a bunch of training data, like x1 is your feature vector, y1 is your label. So you get a size, suppose your training data size is D. You have this D-sized, x is your feature vector, and Y is your label. You get this many data sets. Okay? And you have these data sets, you try to train it, and mathematically is you take this one as input. And what you want to find is a hyperplane, okay, which can maximally separate these data, the known class label, the trained data. And also you can expect that you can minimize the classification error for the new data, for unseen data. And how to work out this one? This plane, people actually call this is maximum margin hyperplane. That means if you can work out from mathematical equation-wise, you can work out this plane. Essentially, is you calculate this maximum margin hyperplane. How to calculate it? Okay. Actually, I will not get into very detail because if you really want to calculate this one essentially is you calculate they call Lagrangian, equation. You calculate this one. This essentially is quite a mathematical optimization thing. Okay. In principle, if you take any math class discussing this optimization thing, they are going to give you very details, but it involves lots of math. Here in this class, that's exactly why the advanced section, I make it not long because I only cover it conceptually, but not cover it mathematically. This is a really mathematical equation you calculate. Okay. So then if you look at little, I just give you a very simple one. You probably can see what is a real thing is you basically get a W is a vector. You can think it's a vector of the weights. Okay, and this X is really the input vector features, input feature vectors. Okay, so you say this cross product, this dot product, W times X, essentially is for each X you put different weights. Like X1, you put W1, you put it as a weight. This adding together this equation. This you can think is a hyperplane, so-called hyperplane. Everything looks like linear because x1, x2 look like linear. But in the hyperplane, it's linear because you have, if you only have one, of course, it's a line. But you have 2 dimension, you get a plane already. Then you get an n dimension, you think it's an n dimension hyperplane. Okay, so that equation itself is n dimensional hyperplane. Then, because you have a class label, the class label you can think +1 is you write an equation is for 2 dimensions. You can think this is essentially is W0 is your coefficient. You can think is this one. Then you get W1, X1, W2, X2. Essentially is this one. Now, if you get a positive label, you think you get inequality is greater or equal than 1. Okay. If it's negative label, you will think this one is less or equal to -1. Then you get a set of equations like this. Your training data essentially is this group of equations. Okay. Then what you want to calculate, you try to calculate the support vector, means you try to calculate which these group of things were sitting at the outmost region. Then you can, or you can say innermost, depends on how you view it, right? Then what you do is you were thinking this one is quadratic optimization problem. It is essentially the convex quadratic optimization problem. Okay. Then you take this, you can do quadratic programming. You try to calculate this Lagrangian multiplier. And that part, you really need to take another course. Okay. For example, if you really want to know this optimization, convex quadratic optimization thing, the best course I probably can recommend you is Stanford University, I think, Steve Boyd. He actually online on Coursera, he has one on this optimization called convex optimization techniques. I think there's a course in Coursera as well. Okay, and that book itself is also very thick, very mathematical. Okay? It's about probably 400 or 500 pages. Those texts. Okay? So you can take that course. They will give you very detailed on how to do different kinds of convex optimization. But of course, in ECE, I think some statistics, they probably will cover these optimization methods, including general engineering here. You probably want to take those courses to know better. I believe the general engineering, industrial engineering, they do have several professors teaching this optimization. Okay. Now we get into linearly separable or non-linearly separable. Remember, not everything is linearly separable. I give you a circle or a ring. Okay, say inside this is positive class, outside is negative class. You will not be able to draw a line to separate it because the whole class is a ring, right? Or it's a circle. Then how could you do this and still work out a linear separable hyperplane? Actually, in many cases, you will be able to map this one into even higher dimension space. That means in 2D you cannot separate. What about I map it into higher D? Okay. Here I just give you a simple example. Suppose you get x1, x2, x3. You originally thinking you will not be able to separate it in a linear way. But you can map this one. For example, you think about a circle. Circle essentially is quadratic equation. Quadratic equation means if you say y equals x something, you will get x squared something. Okay. Then you will not be able to draw a line, say y equals x, you can separate. But what about I take this x squared, I create a new variable. Say this is not x squared, it's x2. Okay. If you think about it, originally you have x squared, now you say x squared actually is another variable. Then you map into higher plane. In that higher plane, this one is linear, right? Because it's not square anymore. Because you take the square, you just say this x squared is x2. You get a new variable, then you get a new dimension, and in that new dimension it becomes linear. So that means if you think about it here, suppose this equation is you get x1 squared. You say this is nonlinear. Okay, it's quadratic. But what about I map this one into a new variable? Once I map into a new variable, everything is linear, right? So that means actually some cases in the low dimension, you say there's no way I can linearly separate it. I map into a high dimension space. I can work out a hyperplane to linearly separate. So in that sense, actually, as long as you are not afraid about higher dimensions, then almost everything can do it in a linearly separable way, right? So that means the SVM, the linearly separable, actually becomes quite realistic. Not like you have to use a very complicated curve to do it. So this is general idea of support vector machine, why you just need to compute those maximum margin hyperplane, which is like a linear plane. You actually will be satisfiable because you can map this into the nonlinear to linear. So to that extent, the support vector machine actually is quite efficient in a high dimension space. You calculate this one, then you are not afraid even the high dimension data. You can work out a pretty good class. Okay. That means the support vector can do high dimension space. But a support vector machine has one problem is if you got the number of support vectors too many, actually, that means you get many, many training data, you get lots of training data, you actually will calculate very slow. But you get very high dimension data, they actually can calculate very fast. So the problem becomes, it's scalable in dimensionality. That means in high dimension, it is scalable. But if you give me many, many training data, you give me lots of training data, you try to calculate those equations. That takes a long time. You can, conceptually you can think about this. Is you try to do we just say that you probably know the linear equation you can transform into a matrix. You can do computation. But if you want to compute this matrix in a very, very, very big one, that means you get many, many lines. You try to calculate this one, you will say it will take a long time to compute. That's the same thing. You get many, many training examples, you got a long time to compute it. Okay. So, but later I'm going to show you SVM is very efficient in high dimension data, but you get lots of training data, you need scalable algorithms. Another interesting thing is about those mapping functions. They call kernel functions. That means once you get a nonlinear data, you want to do mapping. What is the best mapping function? Okay. People actually work out many mapping functions. Those mapping functions they call kernel functions. Okay. Kernel function simply says, you give me this one function. I will have some way to separate them, to give you like a multiplier of the two things. So that means mathematically, if I apply those kernel functions, I will be either transform them into linearly separable things. Okay? And the kernel function, the most popularly used kernel function, there are three. I will show you. One called polynomial kernel function, using this function. Another one called Gaussian radius. They call radius-based function. Most people call the Gaussian RBF. Okay, RBF is radial-based. If you use, people say, oh, I just use RBF kernel. This is RBF. Okay. And another one is the sigmoid kernel. Sigmoid kernel written in this form. But I'm not going to get you into very detail because we did not discuss this computation here anyway. That means you use quite a few popularly used kernel function, and you can actually use this mapping into very complicated high dimension space. You can map them into nice kernel function. You can solve them efficiently. Okay. Then you may say, you did not teach me math. You just teach me those ideas. What's the use of it? Actually, it's quite useful in the sense, even you do not really know how to compute it, there are lots of open source, open SVM functions online. You can download many of them. Okay? And as long as you know the general idea, you know how to use it. You just say, this is very powerful. They can do a very good classification. You get the results. You know this idea. You know these kernel functions. You actually can go down to those open source. You download it. You can use it in a very nice way. There are many medical doctors. They actually do this. I ask them. They say, I do not even know anything about this quadratic optimization, but I just use it in my daily life. Okay, they use it very regularly. Yes. Okay, about the final exam. Okay, final exam, I only test the ideas. Okay, I do not test anything on the, including all these three things I discussed is a very, very high level. In the sense, I'm not going to test anything on the math, including neural networks and including this one. No math, no really using this function to calculate anything, but just ideas. You know what is the idea of this support mechanism. Now, I just said, you know the high dimension data you can calculate very efficiently. Then the problem is, if you got lots of training data, nowadays it may not be hard to get lots of training data. You get lots of training data, the support vector machine will run really slow. You think about it, you get 1 million objects, you say training data. That means you try to compute 1 million things to get an equation sorted out. that you think you get a 1 million simultaneous equation, even they are linear. To calculate it will take a long time. So that's the case. Now I'm going to just introduce you one interesting algorithm. Suppose we get lots of training data, whether we can calculate it efficiently. That one happens was UIUC's work, was by one of my previous PhD students. Now he's a professor in Korea. He actually, when he just graduated, he became a professor in University of Iowa, not too far away. But a few years later, he moved back to Korea. Now he's a full professor, I think, in post-tech, which is one of the highest-ranked Korean universities. And what he did is try to make SVM scalable in a very high number of data objects, training data. So if you get thousands or millions of training data, can you do it, still do it efficiently? Okay, people in the past, they just do sampling. They just say, you give me too much training data, I probably sample something, I construct one. And he wants to use more data, not doing sampling, but still get a better classifier. Okay. Then what he did is called clustering-based SVM. What is clustering-based SVM? I probably give you a little example because we are going to discuss clustering anyway in the next chapter. Okay. So here I just assume you know a little on clustering. I do a little hand waving. You'll see how this clustering can help support vector machine construction. Okay. Let's look at this. This is the picture he was using. Okay. General philosophy is this. You got lots of training data. They give you a positive and negative label. Okay. That means you get hundreds of thousands, even of millions of training objects. Okay. Then what you can do is you first get it. Some is positive, some is negative. You know these are the two groups of training data. For each positive and negative, you try to, because you have lots of training data, you try to construct clusters. Cluster look like this. Okay. Suppose this one is negative cluster. These are the positive cluster. You group things into clusters. And you can group the things into clusters in the hierarchical way. Hierarchical way means you have so many points, they are positive or negative. What you can do is these points, you can group them into, you can think about it. Suppose you go to beach. The sand may have different colors. You say, I want to cluster sands to do classification. Okay. How sand? There's so much sands, right? You get a beach, you get miles of sand. How could you do it? There's just too many points. And what his philosophy, you group those sands in. You take those sands. You say they're very close. They are in the same class. I group them into bigger one. Now you can think this one is a baseball. Okay, because you group the sands, you say these are one class. But baseball is still, the beach is so big, you get a baseball is still, there are so many baseballs now. Think about this. Then you say, what about I further group? They are close, they are in the same class. I further group them into beach ball. And those beach ball is bigger, right? The beach ball can even group into the much bigger one. Now he took those much bigger ones. Now he's going to work on it. Because originally there are so many. There are millions of them. But once I group them into a pretty big one, there are probably only hundreds or thousands of them. Then I can work on my SVM. Right? What he was doing is he grouped those different classes into very big balls. And he will say, this ball is positive, this ball is negative. I try to use smaller number of balls to work out support vector to work out this hyperparameter. Okay. And these numbers are much smaller. Originally you have millions. Now you may have only hundreds. You can using this tree and you work out one. However, okay, this ball is too big. You may make more mistakes, or you say it's too rough. He said, I'm not stopping here. What he first worked out this line, then what he did is this. He says, I group the ball in two big ones. I draw a line. But this line may not be the best line because the ball is an approximation. Right? Then what he did is he draws the line. He says, anything along this line, I want to look at it more seriously. Okay. Those far away from the line, fine. It's more like you think about it, is Hillary and Trump as a vote. Right? Why are they focusing on those swing state? They say, oh, California is for Hillary or Illinois is for Hillary. Trump or Hillary, they do not come here. Okay? Because they want to work on those support vectors. That means those vague things right at the boundary, right? Those are very, very red or very blue. They don't care. They say those are the things, done deal. Okay, they don't care. They care those swing states, right? And once they get into these swing ones, they want to be serious. What is serious? They break those big balls into small ones. Okay. Remember, the boundary ones is small number, okay, comparing to the big other solid ones. Small number, you take those ones, you draw those lines, say anything on the boundary, they are swing, right? Then they say break them apart. This is more like you think about Hillary or Trump. They say break down into every city, every county, go down there and do the campaign, right? That's the same idea. That means you break them apart, they show the small ones. Then you take those small ones into consideration, but you still compute the smaller ones. Remember, if you take the whole U.S., you break down into county, how many counties? You get lots of counties, right? You don't have time to go to all those counties. But if you only focusing on those swing states, suppose you only have like 5 or 10 swing states. You go down there, you break them down into cities and counties. You can go to Cleveland, you can go to Philadelphia. That worth it, right? You don't have to go to Chicago. That's the same idea. That means you go down there, you break them down into smaller ones. Okay, you recompute your support vector and recompute your hyperplane. Is that clear? Yes? Yeah, I think I probably can explain that again. At the very beginning, there are just too many things. It's more like you get too many people in the U.S. you want to vote. Hillary or Trump will not go to everyone, right? Because they don't have time, right? So what they do is they bundle them into bigger ones, into states. You can think of that. Once they bundle them into states, they're solid blue or solid red. You don't have to care. You compute the support vector. I mean, you compute something in the margin, right? Right sitting at the margin. And you compute in a larger one, but you only have a few things to compute. That means at this one, you think about the U.S., you got 50 states, right? You only compute it in the unit of 50 instead of 1,000 of them. Right? That's the first round of computation is on the very big ball, okay, like state. Then once you compute this, you know these are the swing ones. These are on the boundary ones. That's the one is a little risky. You will separate. You will go down one level. That means go down from state, going down to the county, right? City and the county. Then you calculate this. You try to redraw your boundary. That means you originally computed this way. Now you say, no, this is not good because you look at the boundaries here. There are almost no points. These are the points. You recompute those points. You redraw the line. That means you compute one level deeper. You redraw this. I mean, at the very beginning, because these are the approximation. You go down one level, you get a little more detail. Then your calculation on those points, you find they're a good support vector, then you redraw this line will be better. But every round you compute, you only focusing on things at the boundary. And you don't have to compute those points. Those are already done. So you still compute a small number. Is that clear? Yes? The new one, you say, this new one is intersecting with the bigger bars. Yeah. Actually, you see, the original one, you have the separator here, right? When you change it, the separator will change. The change doesn't mean, you can think about this. While you redraw it, you find the boundary is different. The boundary is different means in another round, even this bar may be affected. You have to look at down in a little detail, right? This is more like when you look at, of course, in the U.S. election, the calculation is based on the states. It's not exactly like this algorithm. This algorithm is actually based on everything, right? But if you think about it, even you get a swing state, you go down there and say, oh, this state is not safe anymore. You're based on the new standard. Then you may go down to that state to do the campaign as well. That means you have to break this one down in the next one. Simply says your swing state computation, original computation algorithm is not very good. You probably want to, once you tilt it, you found that this state is not safe anyway. You may want to go to that state to do the campaign. Right? So that's a similar idea. Okay. So that general philosophy, general philosophy is you don't want to spend too much time compute everyone, just too many things. It's very slow. Okay. You first do clustering, which is reasonably efficient. You group them in the layers, hierarchical clustering. You group them into the top layer. They are smaller number. You compute the support vector and the hyperplane in a very quick way. While you do this, you find those things on the boundary. You break them down into lower layer. You find this more refined things. Then you want to do another round of computation. You find a better separate, better hyperplane. Yes. Mm-hmm. Okay. Yeah. You're suggesting something like a random forest. You can randomly pick up something, or even pick up something in a more desirable way. But remember, this algorithm is not a random forest. It's a really rigorous quadratic optimization algorithm. Right? They really do not do the random forest. Random forest is you try to get many forests to finally, many trees to finally vote. This one is just one hyperplane you have to give me. One set of support vector you have to give me. Okay. So that's the one. That's why when you do this computation, you have to think about it in a different granularity. And his general philosophy is you get a multi-granularity. At the very beginning, you only compute at the top rough granularity. Okay. Then you compute a hyperplane. You will find the thing very close to the hyperplane you need to examine. You break down into one level deeper, more refined thing. Then you do the computation. Then you keep adjusting your hyperplane. Okay, finally, you get probably the best hyperplane, which is almost as equivalent to you take all the grains in a very refined level. You do the computation. Basically, he wants to say, my computation is as effective as you put all the millions of data inside to do the computation. Okay. So that's a philosophy, and you probably can see the results because his philosophy has to be tested. Okay. What he shows is this. Okay. You can see he really put this is 100,000. This is like 100,000 original data points, and he wants to find those hyperplane, try to compute this. What he did was he first constructed a multi-layer, this kind of hierarchy. And if you see that the interesting thing is this. If you do random sample, that's what the original people did. Say just too much data to compute. What about I do random sample? You do random sample, there's one problem. You can see, if you want to do classification, suppose, those are the points you want. They are more sensitive rather than the far away one. But once you do random sample, you can see is this part, the whole part is quite empty. You want to separate in this way, but you can see the whole part. You can draw these support vector anywhere, but because they are very sparse, dense part you sample dense, you can see your support vector drawing will be very wrong. Sometimes you really touch those points which should not be touched. Just because your random sample, the dense part is still, you get more chance to sample out. And those sparse parts, those sensitive parts, they likely will be left out because you do random sample. Those are very sparse things. You may not even find it. Right? But if you do hierarchical one, you first find where's the separator. Then you only split the separator. Those things at the boundary will play an important role. You probably can see. Finally, you will find those things in the boundary which will help you to draw a line. Right? Here, the boundary is so far, you draw anywhere, it may work. You can draw things like this. You can draw things like this. But here they say, oh, you don't draw it here because that's the separator is here. Right? You can see the differences. And he actually, I did not show this, he actually showed if you really do classification, the classification accuracy you finally find is much better. You use much less processing power, you can find a very good separator. So this is using hierarchy or clustering to help you speed up this support vector matching. Yes. Best classifying is the best thing. You can separate things. Remember, each data point, some are positive, some are negative. Right? Those data points have different class labels. And what you want to find are those typical ones sitting at the boundary in the shape. So when you draw the thing, you can easily separate. Here you probably can see. If you do random sample, the things in the middle will just, because they are sparse, you won't be able to sample it out. The chance to get those sparse points is very low. But if you do his idea, they were focused on the boundary things. You can see finally those support vector will be around here. Right? You can see that's a philosophy. Of course, the detail, you can read his paper. He did have lots of different experiments to show the idea. It is efficient and it's effective as well. But if you use millions of points without sampling, it's just too slow to make it. So this is about a support vector. Okay. Then what I said is you do not need to know the detail. You still can use it. Okay. There are quite a few websites, but there are several very popular implementations. One called LIB-SVM. That means this is SVM's library. Okay. They have efficient implementations of SVM multi-classification. They have new SVM, one-class SVM. They have lots of SVM in different applications, different languages like Java, Python. So you can go down there, you can download it. There's one called SVM Lite. There's a website called SVM Torch. If you Google them, you can download those sources. You actually can use SVM in a very, very flexible way. Okay? Even you have not very deep understanding of the maths. This is about SVM. Okay? So you know it's another very popularly used classification methods, advanced methods. Then we still have 5 minutes. I'm going to get into rule and pattern-based classification. This one originally I was put in the basic chapter. Later I was thinking I better put into the advanced chapter. I put into here. The general philosophy is this. You do classification, you can use decision trees, you can use naive Bayesian, you can use other things. But rules people may like is it's easier to explain. You think about it, you talk to a medical doctor, you give them a tree they probably like, you give them Bayesian, they only see the probability they may not like because they do not know how to explain it. You give me neural networks, support vector machine, all these are just very complex equations and numbers. They have no way to understand what's going on. Okay? Even in many cases, they may give you better quality. They need explanation. Okay? The rule-based classification, nice thing is you can explain. Okay? That means, for example, if you can write down this decision tree rule, say if the age is used, the students is yes, then buying computer is yes. That's very easy for anybody to understand it. So that's why people actually, even you got a deep learning or support vector machine, there are lots of efforts is how to transform them into rules. Because once you transform it into rules, your model becomes explanatory. It simply says people are eager to buy it, they understand it. Then people will think about how to initially work out these if-then rules for your classification. The rules, the if part, people also call rule antecedent or conditions, preconditions. And the conclusion part or the labeling part called rule consequent or conclusion. Then you may get a bunch of rules. Okay. Then they want to calculate the rules coverage and accuracy. Coverage means this particular rule, how many training data you can cover. For example, you give me, say, 60 training sets, 60 training data or training objects or tuples. If you get this rule can cover 30, okay, then the coverage is this number of tuples covered by this particular rule where the number will be 30. If you total have 60, you can cover 30. The coverage is pretty high. You can cover like 50% of your training data. Yeah, I think we actually got it right on time. Later in the next lecture, I probably go through this rule-based classification. Thank you.